Hello, this is Jack Jackson. Let's take one more look at how we can summarize some of the properties of Euclidean quadrilaterals. And we're going to look at it maybe a little bit different way here. We're going to talk about different types of standard types of quadrilaterals and look at their side properties in this first table here. So take a look at this table and you'll see that we have on the left column the most standard types of quadrilaterals that we might study: kites, trapezoids, isosceles trapezoids, parallelograms, rhombus, rectangle, and square. Those are the typical ones that are studied in a college geometry course and in a high school geometry course. Now, we can look at them and look at the conditions they have on the number and position of congruent sides, number of parallel sides, pairs, and the some combinations of those over here in the last column. So um, within the number and position of congruent sides, I have at least one pair of congruent sides. And notice that that's a property that kites, isosceles trapezoids, parallelograms, rhombus, rectangle, and square all have. And kites, you've got two disjoint pair of congruent sides that are uh, adjacent or consecutive, right? Isosceles trapezoid, you got a pair of opposite congruent sides. And a parallelogram, both pair of opposite sides are congruent. And a rhombus, all four sides are congruent. And a rectangle, opposite sides are congruent. And a square, all four sides are congruent. So here we have two disjoint pair of adjacent congruent sides. Now notice that one's a little different. It's got this double X and the different color background here. That is in this case, a defining property of kites, but it is certainly enough to make it a kite. So notice that a kite has that property. So any other special type of kite, like a rhombus or a square, will also have that property, but not true for some of these other cases. Now, we could also have at least one pair of opposite congruent sides. Well, an isosceles trapezoid has that. So does a parallelogram. And of course, any kind of parallelogram, like a rhombus, rectangular, square, will also have that property. But notice these are the gray background, so those are not enough to make them this. So just because you have a pair of opposite congruent sides, it's not enough to make it an isosceles trapezoid or, say, a parallelogram, for example. On the other hand, we go over here to two pair of opposite congruent sides. We see the background here with the parallelogram. This indicates that that is enough to make the quadrilateral into a parallelogram. So all other kinds of parallelograms, like a rhombus, rectangular, or square, have that same property. Now that's not enough by itself to make it a rhombus, rectangular, or square, but it is enough to make it a parallelogram. But notice that if an isosceles trapezoid doesn't necessarily have that property, nor do all trapezoids or kites. And the most extreme example is where we could get all four sides congruent to each other, equilateral. That's a defining characteristic of a rhombus. So a square, being a special kind of rhombus, also has that property. That's not enough to make it a square, but it is enough to make it a rhombus. And there are rectangles that do not have that property, for example. So some interesting things there. How about parallel sides? Well, the defining property of a trapezoid is that it has at least one pair of parallel sides. Isosceles trapezoids, parallelogram, rhombus, rectangle, square, all of those are trapezoids, so they're going to have that same property, but that's not enough to make them these special kinds of trapezoids. It's just enough to make it a trapezoid, period. If you have two pair of parallel sides, both pair of opposite sides are parallel, that's a defining characteristic of a parallelogram. And so these other kinds of parallelogram, rhombus, rectangle, square, that will also have that property. So if we sort of combine some of these, if it has one pair of sides that's both parallel and congruent, that's enough to make it a parallelogram. And so then these other kinds of parallelograms will have that same property. So here are some of the ways that we can break down a side properties and sort of look at what properties do these have, because we can read this different ways. We can say take a parallelogram. It has at least one pair of congruent sides, one pair of opposite side congruent. Actually, it has two pair of opposite sides congruent, stronger. It has one pair of parallel sides. Actually, it has two pair of parallel sides. When we say this has one pair, that means at least one pair, but it actually has two pair. And then one pair, actually both pair of sides are parallel and congruent. And so you can see that. So the square, the most special one, notice it has all of those special properties about the sides, but those alone are not enough to make it a square. Well, any one of these alone is not enough to make it a square. Okay? Now, what if we look at it the same kind of thing, but we look at it in terms of the properties of the interior angles? This one I threw in cyclic quadrilaterals as well. Had I included cyclic in the one before, nothing would have been checked. So a kite has a pair of congruent angles, and they are actually opposite each other. So that's these two boxes are checked. A trapezoid doesn't have any congruent interior angles, necessarily. Neither does a cyclic quadrilateral. An isosceles trapezoid has at least one pair of congruent angles. Actually, it has two pair of consecutive congruent angles. A right trapezoid has at least a pair of congruent angles. Actually, it has a pair of consecutive right angles that are congruent. A parallelogram has a pair of congruent angles. Actually, it has a pair of opposite ones. In fact, it has two pair of opposite congruent angles, and that turns out to be enough to make it a right trapezoid. Notice that two pair of consecutive congruent angles is enough to make the quadrilateral and isosceles trapezoid, and two pair of opposite congruent angles is enough to make it a parallelogram. We proved all these things earlier. I'm just sort of reminding you of that. At least one pair of consecutive right angles is enough to make it a right trapezoid. A rhombus has a pair of congruent angles. Actually, it has two pairs, and they're opposite each other. Because after all, it is a parallelogram. So since a parallelogram has this property, all other special parallelograms, like a rhombus, rectangle, and square, will have those same properties. Notice that a right trapezoid has at least one pair of consecutive right angles. That's going to be true for special kinds of right trapezoids like rectangles and squares. Okay, that property alone is enough to make it a right trapezoid, but not necessarily a rectangular square. And four congruent right angles, equiangular, is a rectangle. That's a defining property of a rectangle, and a square being a special kind of rectangle gives you that. So I'm just saying, well, which ones have at least one pair of congruent angles? Well, that's true for a kite, isosceles trapezoid, right trapezoid, parallelogram, rhombus, rectangle, and square, but not necessarily for cyclic quadrilaterals or just trapezoids in general. So that's dealing with congruent interior angles. Let's look at supplementary ones. Kites don't necessarily have any supplementary angles. Neither do right trapezoids. That is incorrect. Let me fix that. Okay, actually what I had was correct, but I neglected to put in a column here that I want to add, that I've just added here. So at least one pair of consecutive supplementary angles is enough to make it a trapezoid. I still don't have this quite right. Okay, here we go. At least one pair of consecutive supplementary angles is enough to make it a trapezoid, and all of these are trapezoids, so they're going to have that same property. Including right trapezoids here. Okay, and in fact, if it has one pair of consecutive supplementary angles, it must have at least two pair of consecutive supplementary angles. So one of those really just implies the other there, which is probably why I left out that column before. Okay, so trapezoid has, in general, has that property. Okay, if the so this is if you have a pair of consecutive supplementary angles. okay, you'll have actually two pair of consecutive supplementary angles. Well, what about if they are opposite supplementary angles? Well, that turns out to be exactly enough to make it a cyclic quadrilateral right here. And then it turns out that isosceles trapezoids have that property as well. So they are cyclic, as are rectangles and squares. When you're talking about uh, a parallelogram, what's interesting thing about that is any pair of consecutive angles are supplementary. So it's sort of if you want to think of it, sort of like a trapezoid with either set of opposite sides being considered the base as being the parallels, right? So that turns out to be enough to make it a parallelogram. And of course, certain types of parallelograms, all types of parallelograms will have that basic property as well. So that will be true for rhombus, rectangle, and square. So again, we can sort of read this two ways. Which ones have at least two pair of consecutive supplementary angles? Well, that would be trapezoids and all special kinds of trapezoids, including isosceles trapezoids, right trapezoids, parallelograms, rhombi, rectangles, and squares. Uh, which ones have any pair of consecutive angles supplementary? That's enough to make it a parallelogram. So other types of parallelograms have that property as well, special types. If you have two pair of opposite supplementary angles, actually if you have one pair of opposite supplementary angles, you get two pair of opposite supplementary angles as well. Okay. All right, so that makes it a cyclic quadrilateral. And once again, if it's one of these with the double X and the different shaded background here, that's enough to make it the type that's over here. All right, how about diagonal properties? Let's do the same sort of thing for diagonals. Here I have a convex quadrilateral, kite, trapezoid, isosceles trapezoid, cyclic quadrilateral, parallelogram, rhombus, rectangle, and square. The first thing is we'll do the diagonals intersect or not. And the diagonals do intersect. That's exactly enough to make it a convex quadrilateral. Not actually the definition of a convex quadrilateral, but it turns out to be exactly a good way to uh, uh, get there, right? It's a sufficient condition. And in fact, all of these following are convex quadrilaterals, and their diagonals will intersect. Trapezoids, including special kinds of trapezoids like isosceles trapezoid, parallelogram, rhombus, rectangular, square, and also cyclic quadrilaterals. All of those have to be convex and their diagonals intersect, but it's not necessarily true for a kite. We've seen both convex and concave kites. If the lines containing the diagonals are perpendicular to each other, that that will definitely happen in a kite, but that's not enough to make it a kite. So special kinds of kites like rhombus and square, not rectangle, rhombus and square will have that property. If the line containing one diagonal is not only perpendicular but actually bisects the other diagonal as well, that turns out to be enough to make it a kite. And so other special kites like rhombus or square will have that property as well, but not true for these other types. Well, which ones have congruent diagonals? Well, that's a property that isosceles trapezoids have. Notice it's not enough to make it an isosceles trapezoid, but it is a property that isosceles trapezoids have. So special isosceles trapezoids like rectangles and squares will have that property. We didn't really talk about this one a whole lot earlier, but this is kind of an interesting thing. The diagonals intersect so that the pieces are proportional in length. That's true for isosceles trapezoids, and it's also true for parallelograms. In parallelograms, they actually uh, bisect each other, right? Which we'll talk about over here. Uh, so that's true for a rhombus, rectangle, and square, but in isosceles trapezoid, they don't bisect each other, but the pieces are proportional in length. If you have one diagonal as an angle bisector at both ends, that is enough to make it a kite. So a rhombus and square being kites have that same property, but none of the others necessarily have that property. If both diagonals are angles bisectors at both ends, that's enough to make it a rhombus. All kites don't have that property, but a special rhombus like a square does. If you have one diagonal bisects the other, that's true for a kite and a parallelogram, and these special kinds of parallelograms down here. But if both diagonals bisect each other, that is enough to make it into a parallelogram, and these special kinds of parallelograms have that property. Next, let's look at a similar table for symmetry. So some quadrilaterals have certain types of symmetry properties. So if it has reflective symmetry about at least one diagonal, or the line containing one diagonal, then it has to be a kite. So a rhombus and square being a kite have that property as well. If it has reflective symmetry about both diagonals, then it has to be a rhombus, including squares. Okay, so that's a property that all rhombi have, including all squares, but that's not enough to make it a square. It is enough to make it a rhombus. If it has reflective symmetry about at least one line that goes through the midpoint of opposite sides, that makes it an isosceles trapezoid. So that's a special property that isosceles trapezoids have that actually guarantees that it's an isosceles trapezoid. And a rectangle and square being an isosceles trapezoid have that property as well. If it has reflective symmetry about both lines through the midpoints of opposite sides, then it has to be a rectangle, and that includes squares. Now, not only can you have reflective symmetry, you might have rotational symmetry. And if you do that, it's going to have to be about the intersection of the diagonals, and the diagonals are actually going to have to intersect each other at the midpoints. They're going to have to bisect each other. So that makes it a parallelogram. So really the only way you can have rotational symmetry is if you have a parallelogram, and they will have a rotational symmetry about the midpoint of one of the diagonals, which is also the midpoint of the other diagonal, and the angle will be pi radians, or 180 degrees. And so that's enough to make it a parallelogram, and these other special kinds of parallelograms have that property. But a square has even more special uh, rotational symmetry that the others don't have. It actually has a rotation not only by an angle of pi about that same point, the center point there, but also a rotation by pi over 2. Of course, it has a rotation by pi over 2. It also has a rotation by any multiple of pi over 2. So that'll be a rotation of pi over 2, a rotation of pi, rotation of 3 pi over 2. Or, of course, any figure is going to have a rotation of 2 pi. That's not really special symmetry. Okay, so this video gave you a little summary of some of the main properties of Euclidean quadrilaterals, and it sort of gave that in a little table form, a little bit different way to look at it. And this summarizes some of the things that we've studied in more detail in our earlier videos. If you want to see pictures of these dynamically, go to my GeoGebra activities, and you can see these properties played out visually as well. And you can see that in the earlier videos in this playlist.